All right. I think everybody is back. Let's try to be on time. This is only day one, so let's be on time. Let me introduce Jonathan Selinger, our next speaker. Jonathan Selinger is a professor in Kent State University in Ohio. In fact, he's the professor when I was there. He taught me the first class in the entire PhD program. And his course on that class was statistical mechanics and has been recently published in a book. So that is one of the reading material you should read. It's a very reader-friendly book. So Jonathan received his both bachelor and PhD from Harvard University. Then after that, he moved on to do postdoc with Dr. Brusma, who just gave you the lecture earlier. And then after that, he went to take a job in the, he worked as a research physicist in the Center of Bio and Molecular Science and Engineering in the Naval Research Lab. Then in 2005, he moved to Kent State, and a few years later, I was there. So I was very lucky to have Jonathan as one of my teachers of the very fundamental grad level class. I hope you will be enjoying his lecture as well. Thank you. So I will give the stage to Jonathan.
Thank you very much. Does it work with this mic? I did the wrong mic. Okay, can you hear me all right? Excellent. Thank you so much, Shuang, for the introduction. Thanks to all the organizers. I'm so glad to have the opportunity to speak with all of you here. So in this series of lectures, I'm going to talk about the physics of liquid crystals. That is to say, phases of matter that have order that's intermediate between regular three-dimensional crystals and ordinary liquids. So that is materials phases that are characterized by some kind of orientational order, right? Intermediate order, but not the full 3D crystalline order, as I shall show you. Okay. So the plan of these talks is what's written up here. Okay, so I'm going to begin with an overview of what are liquid crystals, talk a little bit about the optical consequences of liquid crystal ordering, which is how these materials are normally used, and then go into the statistical mechanics of the phase transition from liquid to liquid crystal. In the following classes, I'm going to talk about elasticity, then about defects and solitons, and then about modulated phases of liquid crystals. Okay. So I prepared this series of 4, but then when I was preparing them, it worked out that the first 2 were a little bit shorter and the second 2 are a little bit longer. And so if I finish early, I'm going to go on to the second one so that I can save up time for the last 2 that are longer. Okay, so the references that I put here and also up on the summer school website are these 3 things that I've written. The first is a book corresponding to the class that Shuang took. So that's an overview of the theory of soft matter leading up to liquid crystals. And then are a couple of articles, review articles that I've written about elasticity and about modulated phases in liquid crystals. Work about defects is, well, that's a book that I'm writing this year. And so that'll come out next year, I hope. And you can buy it then. Ha ha ha. Okay. Right. Okay. Moving on to the general subject. Okay, so liquid crystals. These are phases of matter with some partial order. Okay, so more order than isotropic liquids, less than conventional crystals. Okay? These are typically composed of long organic molecules with the structure that's shown here. Okay? So this is the most chemistry I'm going to show in the whole 4 classes. But this is meant to be a molecule with a couple of benzene rings, and it has this cyano group at one end, and it has this alkane chain at the other end. So this corresponds to one of those zigzag chains that Robin Brensmo was showing you in the previous class. Okay? And if you want to take a coarse-grained physical view as opposed to a molecular view, you might say that this object looks sort of like an arrow. Okay? So it has some characteristic orientation, right? It's pointing in some direction. And then, if you have a large population of such molecules, you could ask, what's the distribution of orientations of these arrows? Right? So are they pointing at all random directions in space, or are they all pointing in the same direction? Or do they have some statistical ordering, like a ferromagnet? Okay? What often happens is that you get ordering as illustrated in this little cartoon. That is, you have order along an axis. So it's similar to a ferromagnet, but unlike a ferromagnet, you have molecules that are pointing in both directions on the axis, right? About half of them pointing this way, half of them pointing that way. Okay? So you could describe the whole distribution of orientations by a double-headed arrow, like this, right? That illustrates what's the axis along which the molecules tend to be pointing. Okay? And so they're not pointing perfectly along this axis, but mostly. This is what's called a nematic liquid crystal phase. So this is the most common kind of liquid crystal that's in most display devices. Okay? And this double-headed arrow is called the nematic director, and it's represented by a unit vector n hat. Now, if we continue to look for a coarse-grained description, and we want to zoom out even more, we could say that's the description of the order that's here. But what about in other positions? What happens over longer length scales or time scales? Okay? The order might vary as a function of position. Okay? So you might have the molecules that are ordered, in this direction over here and in this direction over there. Okay? So that the director can vary as a function of position or as a function of position and time. Okay? So you understand now that each of these double-headed arrows represents a local average, right? That there are thousands of molecules that are getting averaged to make this symbol, and thousands more here and thousands more there. Okay, but the population is gradually shifting in its average orientation as you go along as a function of position. Okay. So it might be non-uniform. It might be changing in time to be dynamic. Okay? This is the kind of thing that liquid crystal physics studies, right? What controls the orientational order? So what controls the average direction of the molecular alignment as a function of position and time, as well as what controls the magnitude, that is the quality of the molecular alignment that goes into any of these averages. Okay. Whoops. Now, there's I mentioned that the nematic phase is the most common liquid crystal phase. There's all kinds of variants on that. Okay, so here's just a list of some of the varieties of these. Okay, So pneumatic, that means that the director on average is uniform. Okay? It might be distorted away from uniform if you push one way on one part of the cell and another way in another part of the cell. But on average, it tends to be uniform. Okay? There are variations on that where the orientation tends to be modulated. That is, even if you let the molecules do whatever they want to do, they tend to have a variation in the alignment. Okay? So in the cholesteric liquid crystal phase, also pretty common, the director is in a helix. That is, here it points this way, and then as you go up, it points this way, this way, this way, this way, right? And it keeps rotating around. Then there are more exotic variations. There's a twist-bend pneumatic phase where the director is in what might be called a conical helix. That is, it's not perpendicular to the helical axis, but it's at some cone angle with respect to the helical axis. And then it rotates around that cone as you go up. There are blue phases which have a very complicated cubic lattice of double twist tubes. So there are tubes in which the director has a twist, as I will show you later, and then those tubes are arranged in a cubic lattice. Okay. There's a recent discovery of a ferroelectric pneumatic phase. So that is a phase where you don't have order, which is 50% pointing one way and 50% pointing the other way, but there is a vector order, right? That the molecules are actually pointing this way and not that way. Okay, that's a recent variation that I'm not going to talk about actually in these 4 classes. Okay, so that's a family of phases that are characterized by orientational order, but their positions are still random. So these are all still fluid phases where the positions of the molecules are random, so the whole structure can flow. There is another family of phases called smectic phases, where the molecules tend to lie in layers. Okay? And so when they form layers, that makes what's effectively a crystal in one dimension, but it's still fluid in the other 2 dimensions. Okay? So it could look like a crystal in Z, where there's a periodicity in the density, right, with more molecules here and not so many there, and then more molecules and then not so many. Okay? But still, within the XY plane, the positions are random. Okay? So it's partially a crystal and partially fluid. Okay? Then, if you want to categorize even more, you could say in the smectic A phase, the orientation of the molecules tends to be perpendicular to the layers, right, along the layer normal, along the wave vector. By comparison, in the smectic C phase, the director tends to be tilted over. That is, the molecules are not vertical, but they're tilted over. So they still have horizontal layers, but the individual molecules are tilted. And then there are other variations with different types of internal order within the layers. Right? There's also a family called columnar phases, which are like crystals in 2 dimensions and liquid in 1. Okay? So they're crystal in 2 dimensions, so they lie in columns. Okay? And then they're fluid within the columns, going up and down in the columns. So it's quite a variety there. I'm going to concentrate on pneumatic phases in the first 3 of the classes, and then go into more of the variations in the 4th one. Now, the reason why this matters, the reason why people care about the orientations of molecules is that that has big implications for the optical properties of liquid crystals. Okay, so here is kind of a schematic illustration of what happens when polarized light passes through a liquid crystal cell. Okay. So in this picture, right, this is meant to represent a polarized light, right? So light is propagating from left to right, and then there's an electric field which is going up and down, and a magnetic field which is going in and out of the screen. Now, suppose that encounters a liquid crystal, okay, where the molecules tend to have some orientation. Okay. One possibility is that the orientation of the molecules might be parallel, might be perpendicular to the polarization of light. Okay, so here the polarization of light, it's going up and down, and that is perpendicular to the average orientation of the molecules here. So as the light passes through and the electric field is going up and down, it tends to push the electrons around. Okay? But it's pushing the electrons around within the molecules across the short dimension of the molecules. Okay? So the electrons can't go so far. Right? So when the electric field comes in, it induces an electrostatic polarization in the molecules, but kind of a small electrostatic polarization. Okay. By contrast, when the light passes through this kind of liquid crystal cell, okay, as the electric field goes up and down, it tends to push the electrons up and down along the long direction in the molecules. Okay, so it can push the electrons farther. So you get a bigger electrostatic polarization in this case than you did in this case. All right? So that means that you have a different dielectric constant for the polarized light, right, in this case compared with this case. And a different dielectric constant means a different index of refraction for the light. Okay? So for this anisotropic fluid, the liquid crystal, there's not a single index of refraction, right? There are different indices of refraction depending on how the polarization is oriented with respect to the nematic director. Okay. This one is called the ordinary index, NO, and this one is called the extraordinary index, N sub E. That has important consequences for how light passes through a liquid crystal. Let me illustrate that with an illustration of an experiment. Okay, so here's an experiment where somebody puts a liquid crystal between cross polarizers. Okay, so on the bottom, let's say that there's a polarizer which is oriented in the phi direction in the xy plane. And on the top, let's say there's an analyzer which is oriented in the phi plus 90 degree direction in the xy plane. Okay. And now light is going to pass through, and it gets polarized, and then it propagates through the liquid crystal, and then it goes through the second filter. Okay. So if there were no liquid crystal there, I'm going to step around this way so I don't have to bend so much to see the screen. Okay. If there were no liquid crystal there, then you know what would happen, right? The light would be completely blocked, right? And so if it were an ordinary isotropic fluid that's between the polarizer and the analyzer, okay, the light would come in here, it gets polarized, and then nothing gets through the second filter. However, what happens if it gets into the liquid crystal here? Okay, we can analyze this using this technique called Jones matrices. Okay, that is, suppose you represent the polarization state of the light by a vector in the xy plane, right, showing the electric field direction in the xy plane. Okay. When it passes through this the first polarizer, then the electric field gets projected onto this unit vector, cos phi, sin phi, okay, indicating the orientation of the filter, okay? So you can do this projection, right, by taking the dot product of the electric field with this unit vector and then multiplying that by the unit vector itself, right? That's the same thing as having a 2x2 matrix acting on the electric field. Okay? Then you say, what happens for the light that's propagating through the liquid crystal? Okay? Well, the phase of the light advances, right, as it passes through this medium, and the phase advances by an amount which is the index of refraction times the distance d divided by the wavelength of the light. Okay? But we know that there are different indices of refraction for light in the x direction versus the y direction, polarized in the x direction versus polarized in the y direction. Okay? And so that's represented by a matrix, 2x2 matrix, with these two different complex numbers in there, right, showing how the electric field phase changes. Then you multiply by another 2x2 matrix, which represents the projection onto the direction of the second polarizing filter up there, okay? And remarkably, the result is not zero, right? If you just multiply out these matrices, you don't get zero, but instead you get a non-zero optical intensity, right? So an optical intensity proportional to the electric field squared, okay, which has this interesting dependence on two of the liquid crystal parameters. Okay, so part of the dependence is on the difference between the extraordinary and the ordinary indices of refraction. Okay, so if that difference is zero, you get zero optical intensity. Okay, but if that difference is non-zero, then you do get light that passes through. Okay, and the light that passes through then is proportional to the sine squared of 2 phi, right, where phi is the angle between the polarizers and the director, okay, the axis, the favorite axis of the liquid crystal. Okay, so the point of this is that if you do anything to change the director orientation, then you'll change the optical intensity, right? So if you change the director orientation in the xy plane, you'll change this phi angle. And if you change the orientation out of the xy plane toward the vertical, you'll change the delta n. You'll change the effective difference in optical properties between light polarized in the x direction versus the y direction. Okay. So that in a nutshell is what goes into building a liquid crystal display. Right? The idea in a display is you want to put on an electric field which is going to change the alignment of the liquid crystal, and then that will change how much light can get through a cell between crossed polarizers. Okay? So that's the basics of how the first liquid crystal displays were built for calculators, for digital watches, things like that. And then there are more complex refinements of that for modern LCD TVs. Okay. But they're all based on this concept, right, of determining how much light gets through, right, changing how much light gets through. The output of a liquid crystal display is polarized light, right, as you could see from this argument. And so, you could try looking at an LCD with polarized sunglasses, right? And, it works if you say, hold your digital watch up in the normal orientation and wear sunglasses in the normal orientation, right? But if you tried rotating your sunglasses by 90 degrees, you wouldn't be able to see anything, right? Because it all gets blocked. All right, so that's kind of an overview of this field of liquid crystal science, right, of what it is that people want to control, the distribution of molecular orientations and the alignment of molecular orientations, and then the optical motivation for why they want to control it. Okay. So let's move on now in thinking about the physics and consider, how do we describe this orientation, right? What sort of order parameter do we want to use to characterize the distribution of molecular orientations, right, to recognize that we have a liquid crystal phase? So the notion here is that we have a phase transition, related in some ways to the transition between a paramagnet and a ferromagnet, as some of you may have studied in solid-state physics classes. Okay. And it's a phase transition with spontaneous symmetry breaking. That is, on the high temperature side of the transition, you have more symmetry, less order. Right? On the low temperature side, the symmetry is broken and the material tends to order in a direction which is randomly selected. And so we want to develop an order parameter which will characterize both the magnitude and the direction of the spontaneous symmetry breaking. Okay. So for the isotropic pneumatic transition, right, each molecule has a direction that's represented by a unit vector, right, the orientation of each of these yellow arrows. Okay, so if we want to characterize the transition, we want to calculate the average of something. Okay, so what do we calculate the average of? Okay. Well, the first thing you might guess is, let's average these unit vectors, right? That's what you do in the theory of magnetism, right? If you have a whole bunch of dipole moments, you average all the dipole moments, and that makes the net magnetic order of the material. The trouble is that doesn't work because it averages to 0 in the pneumatic phase, right? Because half of the unit vectors are pointing this way and half of them are pointing that way. So this average would be 0 in the pneumatic phase. So this is a good thing to average for magnetism, but it's not the right thing to average here. Okay. So the point is we want something that's even in the orientation, so that molecules oriented this way and molecules that are oriented this way count the same in the average. Okay. So if you want to average something that's even, maybe you might think, oh, let's make a dot product. We know how to make dot products of vectors. Okay. That's no good. It's no good because these are unit vectors, right? And so if you make a dot product of something with itself, that's identically 1. So it doesn't carry any information. Okay. So maybe you're thinking, oh, well, I know about the cross product. How about that? right? But that's no good either, because the cross product of a vector with itself is identically 0. So that doesn't carry any information either. Okay. What you need to do instead is to average the tensor product, right? So the tensor product is a third way of multiplying vectors, unlike the dot product and the cross product, right? So the dot product takes two vectors and gives you a scalar, right? The cross product takes two vectors and it gives you another vector, really, pseudo vector, okay? The tensor product takes two vectors and gives you a tensor, okay? So it is a tensor that consists of all the possible ways of multiplying the vectors. Here it's written in an abstract notation, but I can write it in a more specific way. Suppose you have, a vector u that's ux, uy, uz, right? And a vector v is vx, vy, vz. Then the tensor product of u tensor product v is a 3 by 3. That's all the possible ways of multiplying them. ux, vx, x, vy, u, x, v, z, u, y, v, x. You finish it for homework. Okay, so, right, that's a tensor product. Okay, so what you want to do is to make the tensor product of the orientation with itself for each individual molecule and average those things. So you get an average tensor, okay? Then you want to know, is the average tensor going to be the same or different from what it is in the isotropic phase? Okay, so what is it in the isotropic phase, right? Well, in the isotropic phase, the tensor averages out to be the identity tensor, right? In the isotropic phase, it averages out to be 1, 1, 1 along the axis times a third, okay? And so you want to know, when you construct this thing, does it come out to be this? If it's this, then you're in an isotropic phase. If it's something other than this, then you're in the nematic phase. Okay? And so people calculate this tensor average, and then they look at that minus what you get in the isotropic phase, this thing. Okay? And typically normalized by a factor of 3/2. Okay. So, question?
Yeah, is there like a intuitive reason why it turns out to be the identity in the isotropic phase?
Let's think about that for a second. If you have any molecule with some orientation, okay, so so this thing is going to be like the average of Lx, okay, and here is the average of Lx, Ly, right? And dot, 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 down to the average of LZ. Okay. If you have any of the non-diagonal elements, okay, then the thing that you're averaging can equally well be positive or negative. Okay, and so it's equally likely in an isotropic material for this average to be positive or negative, and so it will average to 0 in the end. Okay. For any of the diagonal elements, the Lx, this is Lx squared, right? And Ly squared and Lz squared. Okay. And so those are positive things, right? It's a real number squared. Okay. So when you average a positive thing, it's going to come out positive. It can't come out to be 0. Okay. So it will average to be some positive number. Okay. Now, what positive number will it come out to be? Okay. Well, if you take the trace of this tensor, that is Lx squared plus Ly squared plus Lz squared, it's a unit vector, right? So the average, so for any molecule, the trace is going to be the L vector squared, which is 1. Okay, Lx squared plus Ly squared plus Lz squared is 1, and the average of 1 is 1. Okay, so these 3 averages have to add up to 1. And if the phase is isotropic, that is, all directions are the same, then the x direction is no different than the y direction or the z direction. Okay, so you have 3 things that are all the same as each other, and they add up to 1. Okay, so they have to be a third. Okay, so that's how you get this 1/3, 1/3, 1/3. Okay, yes, excellent question.
I'm sorry, so what is Q? This is what we use to normalize the tensor?
Yes, okay, so this Q, so I have this tensor product with itself, okay, so the average of this combination, Lx, Lz, whatever, okay, so I take this thing, okay, minus this thing, okay, so I want to know this combination, is it 0 or is it not 0? Okay. If it's 0, you have an isotropic phase. If it's not 0, then there is some orientational order, okay? And then you must have a pneumatic phase. And I'll show you some analysis of that in just a minute, okay? So I can define a pneumatic order parameter to be this difference. Okay, this minus that. Okay. You could stop there, right? I mean, that's good for a definition. Conventionally, most people multiply this by a factor of 3/2. Okay, and so then they cleverly distribute the 3/2. And now this is negative 1/2, and this is 3/2. Okay, so this thing on the board is, the same as what's written up there. Okay, the 3/2 of this tensor product minus 1/2 of this identity tensor. Averaged, right? So you calculate the tensor and then average the tensor. Okay.
It basically tells us how close we are to the pneumatic phase.
How close you are to an isotropic phase. Right? So it tells you whether you're in the isotropic phase or whether the orientation has been disturbed in some way from the isotropic phase. Okay, so let me show you an example. Maybe that will make it clearer. Okay, if you have an isotropic phase, then this tensor is all zeros, like that. Okay, because this average equals this thing. Okay. For a different example, okay, so suppose every molecule is perfectly oriented along the plus or minus z-axis, okay? Half are pointing straight up, half are pointing straight down, nothing else, okay? Well, in that case, what do we have, right? Well, the average of all the LZs are plus or minus 1, okay? So the average of LZ squared is 1, okay? All these other components here are 0, right? Lx is always 0, Ly is always 0, so this is always 0 times something, okay? So this part of the tensor is 0, 0, 0, 0, 0, 0, 0, 0, 1, okay. I take that, I multiply it by 3 halves. Then I subtract 1 half from all the diagonals, okay? The result is this thing, right? It has 1 in the ZZ place. It has negative a half in the XX and YY places, and it's 0 everywhere else, okay? This now represents perfect pneumatic order along Z. Okay. What if it's not perfect, right? So typically in the world, things aren't perfect, right? Typically in the world, there's a distribution of orientations. Question?
Yeah. So I see in both the isotropic phase and for the perfect pneumatic around Z, the Q tensor is a traceless tensor. So is it always true?
It is always true that it is a traceless tensor by construction, okay? And so I gave you an argument before that the trace of this thing has to be equal to 1, okay? And now we're subtracting off a tensor with trace equal to 1 and multiplying by 3 halves, right? And so we have subtracted off the trace. And so this must be a traceless tensor. Also, it must be a symmetric tensor, right? Because here you have the x times y and there's y times x, okay? So it is a traceless symmetric tensor which has 5 degrees of freedom, okay? Partial pneumatic order along Z, okay? So suppose then you have some distribution of orientations, okay? In that case, the Q tensor comes out like this, okay? That is, that it is closer to isotropic. It is closer to all zeros, okay? So this thing for perfect pneumatic order gets reduced by a scalar called S, and that scalar gets the name of the scalar order parameter, okay? And the interpretation of that is the average of this quantity, the average of 3/2 cosine squared of this angle minus a half, okay? The angle is the angle between each molecule and the director, which in this case is Z, okay? So this average is showing what's the quality of the pneumatic alignment. How well are the molecules aligned along Z, okay? If they're all perfectly aligned along Z or negative Z, then theta is always 0 or 180 degrees, okay? So the cosine is always plus or minus 1. So the cosine squared is always 1. You have 3/2 minus 1/2, that's 1, okay? So 1 means perfect pneumatic order, right? If you have the isotropic phase, then theta could be anything going around the sphere, okay? And the average of this works out to be 0 by basically that same argument that I gave you before about isotropic averages, okay? In a typical experimental liquid crystal, this will come out between 0 and 1. So it's not 0 order, it's not perfect order, it's some intermediate level of order. Okay? So this is like calculating the order parameter of a magnet, right? So if some of you have studied, for example, the Ising model of magnetism, a model where you have spins that are just up or down, then you calculate a magnetic order parameter, which is the average of the spin number, right? Which is something between 0 and 1. Okay? So that shows how well the spins are aligned. Here is the analogous thing for liquid crystals, right? Showing how well you have these vectors aligned along the z-axis. Now, you might say, what if you don't have alignment along the z-axis, but it's along some other axis? Okay? Well, if it were along the x-axis, you know what you would do, right? You would put the 1 in the xx place instead of the zz place. Okay? If it were alignment along the y-axis, you would put the 1 in the yy place. Okay? But those are not the only three choices, right? You might have alignment along any funny diagonal axis, right? Anywhere in three-dimensional space. Okay? And so in that situation, you would say there's order along some arbitrary axis, n. Okay? In that case, the Q tensor is the tensor product of n alpha times n beta. Okay? This thing times 3/2 minus half the identity. And all of that multiplied by this scalar order parameter s, which means how well are the individual molecules aligned with the n-axis. Not the z-axis, there's nothing special about z, but with the n-axis. Okay. So this is the generalization of the thing that I showed you in this slide, right? From order along z to order along any arbitrary axis n. Okay. And the way to work with this is remembering about eigenvalues and eigenvectors. Okay. So the point is, when you're working with a tensor like this, the eigenvalues are s and negative s over 2 and negative s over 2. Okay? They add up to 0 because the tensor has to be traceless, as was the question a few minutes ago. Right? And the eigenvectors are n and any old two vectors perpendicular to n. And so the n eigenvector goes with the s eigenvalue, and the others go with the others. Okay. I can also give you a less mathematical version of this story. Okay, maybe some of you will like that better. Okay, the less mathematical version of that story is to say there are two important issues in pneumatic liquid crystals. Okay, one issue is what's the magnitude of the pneumatic order, right? That is, how well are the molecules aligned with each other along some spontaneously chosen axis. Okay? The other issue is what's the direction of the pneumatic order? That is, what axis did the molecules choose of all the possible axes in three-dimensional space? Okay. So the magnitude of pneumatic order is what's characterized by this S, scalar order parameter, right? That tells you what's the quality of the alignment, right, on a scale from 0 to 1. Okay, that goes into determining what's the optical birefringence, right? How different are the optical properties of the material along the director versus perpendicular? Okay, that is something which people change mainly by varying temperature. I'd say that's about 10% of liquid crystal science. I'm not counting, that's an estimate. Then the other 90% has to do with what's the direction of nematic order. Okay, so of all the axes which one did the molecules choose, okay, that's characterized by this n unit vector, which is an eigenvector of the Q tensor. That goes into this second factor in the transmitted intensity, and it's something that people change in lots of ways, by surface anchoring, by applied electric or magnetic fields, a variety of things like that. Okay, so that's another big issue. That's the biggest issue in liquid crystal science. Okay, how are we doing on time? Is it break time now? I think if you guys, sorry, Shuang?
Yeah, I think we can do a break.
Why don't we do a 5-minute break now for anyone who wants that, and I'll resume, 5 minutes.
5 minutes only, we'll have a longer, don't go to 5.
It's funny to see that the ratio of signs goes proportional with the number of components in a scalar versus a tensor.
The number, say that
For a
again?
scalar, you need one number, right? For tensor, you need 9 numbers. So it goes one proportional to how complicated the
Yeah,
is, right?
sure.
It's something I've always wondered, which I didn't want to interrupt the flow or better to answer a student question. Yeah.
Sure. Great, please.
So it's a bit quirky. So if you want to have it, like I'm interested, if you want to intuitively guess that because the nematic order is 180 degrees has symmetry, could you? I mean, is there an analogy to spins where you have spin 1 is vectors, unit 1 index, then spin 2 indices, for example, I don't know, for example, gravitational waves. Then maybe
I think
another question is what happens if there is not 180 degrees? What if there is 90 degrees symmetry?
Yeah, people talk about these generalized nematic phases. Maybe you've come across those in your work. Hexatic, for example.
Oh, yeah.
Have you seen those things? Right. So that's something that has 6-fold symmetry instead of 2-fold symmetry. Here.
4-fold doesn't exist?
The word for it exists, tetradic, and it exists in some unusual colloidal systems, right? So colloid science is how people normally would adjust these things, right? You could make particles shape like squares, and they might have a potential for forming a 4-fold symmetry phase. The word for that is tetradic. So, so those things certainly exist in 2-dimensional physics. Okay. Now, in 3-dimensional physics, then it would be trickier. Then you would need to use like spherical harmonics to characterize what's the distribution of orientations. Okay. So these things with the tensor order parameter are characterized by spherical harmonics with L equals 2.
Okay.
So it's like what you were saying with gravitational waves, right? So it's the tensor sort of thing, right? So a vector order, like in ferromagnet, right, would be characterized by a spherical harmonic with L equals 1. All right. There could be in principle. Yeah. Oh, absolutely. Yes. That's something that's represented by a tensor of certain rank corresponds to a spherical harmonic with L equals that rank.
So in a sense, you could be, if you were so you wouldn't need to do all these analysis. You would be smart enough and you would understand the symmetry. It could maybe immediately say, oh, we see that this is symmetry. We can immediately say that we need two indices. Maybe something like that.
Yeah. Maybe. I mean, if you're very smart. Or you could say, if there are four directions that are equivalent, like the directions of the vertices of a tetrahedron, right? Then you could call that a tetrahedratic phase.
Oh, okay, that's something.
And then you'd say, well, what kind of spherical harmonic do I need to characterize that? And I think it turns out to be L equals 6. So it's a relatively high spherical harmonic. So you're from Ljubljana? You're are you a student of Miharovnik?
Yeah, he wanted to say hi. Yeah, he sends his greetings. Actually, my mentor, Miha is the head of the group. Simon is my mentor. Oh, you probably know.
Chopar. Yes. Excellent. Great. Glad to meet you. Hi.
Quick question. So,
sure, please.
With your more exotic pneumatic phases, like you mentioned, the directors of Amherst, would you say we could do like a change of basis on this tensor and then interpret sort of the components along? Let's say, suppose you have like I want to use this formula for a different problem, but suppose I have like a spherical symmetry, so I'd imagine in Cartesian coordinates that would just look like an isotropic tensor. But
I think maybe I need to see more about what you're doing. Maybe we should talk when there's a longer time period.
Thank
right.
you.
Great. No, thank you. So you're from Syracuse?
That's right.
Okay, and your name is
Shabib.
Shabib. Great. Let's talk more a little bit later.
Thank you.
Great. Thanks. Hi.
Just a quick question.
Sure.
How do you choose the best course grading for how large to pick your segments to take the director average over? Because you can take like an n equals 1 limit, and then you just have a fluid simulation. So
Yeah. That's a tough question. And it's tougher in simulations than it is in experiments. Yeah. Such a great question. I think we need to go on, but let's talk more in a little bit. Okay, can we continue? All right, let's go on. All right, so going on. Today, for the rest of today, I want to talk about the magnitude, right? And then everything else is going to be about the direction. Okay. So, speaking about the magnitude, okay, so the kinds of things that we might want to understand are what can we say about the phase transition, right, between isotropic and nematic? So the transition between S equals 0 and S not equal to 0, right? And then we could say in the nematic phase, what's the magnitude of the order? So how does the order parameter S depend on temperature? So there are a few kinds of approaches for studying those questions. Okay, one style is the Landau-de Gennes theory. Okay, so the idea here is to think of it's phenomenological, right? Meaning that we're not going to think about the microscopics, but instead we'll just think about symmetry considerations and the smoothness of functions, okay? And use that to get general principles about the phase transition, right? Then there are more specific molecular theories which assume something about the particles that make up the liquid crystal. Okay, so one variety is Meyer-Zaupert theory, which is based on the statistical mechanics of molecules which interact through this potential, right? A potential energy which tends to favor molecular alignment equally well, parallel or anti-parallel. Okay. And then another class of theories, Onsager theory, is based on the statistical mechanics of rod-like molecules with some excluded volume repulsion. Okay. For today, in the interests of time, I can only do one, okay? I'm going to do the first one, and then I'll skip the other two, which, you can read about in my book. Look at you. So I'll just do the first one, okay? So the idea here, it's for Landau-Degen theory, right? So it's analogous to what you might have seen for Landau theory that's been developed in the context of superconductors or superfluids or magnetism, right? So you may have seen, for example, with superconductors, right? So long before BCS came along, right, people had the idea, oh, maybe there's a complex order parameter for superconductors. How could the free energy of a superconductor possibly depend on this complex order parameter? Okay. Same idea here, right? We could say that we believe there's a tensor order parameter, this Q tensor, which has two components and which is a symmetric traceless tensor. And then we ask, how could the free energy density possibly depend on this tensor? Okay. Well, what can we assume, right? So, I mean, at first you might say, I don't know, it could depend in any possible way. Okay, but there are two big assumptions that you have to put into the theory. One is that there's a symmetry, right? The free energy density has to be a scalar, right? That's what a free energy density is. Scalar means that it's invariant under rotation. Okay, so no matter what the orientation of the Q tensor is, if you rotate from having a distribution of molecules mostly like this to a distribution mostly like that, that has the same free energy. Okay. Then there's a more subtle assumption of analyticity. Okay, so that is that the free energy density must be a smooth function of the order parameter. A question?
If there's a phase transition, how does it stay analytic?
The idea here for the Landau theory, not just for liquid crystals, but for superconductors or anything, is that the input into the theory has to be analytic or smooth, but the output of the theory, it turns out to be non-analytic at the phase transition. Okay? So for those of you who have studied the calculus of complex variables, you know about this concept of analytic functions, right? For those of you who haven't studied that, just think in your heads smooth functions. Okay? So the notion is that if you assume the free energy is not a smooth function, you could get anything in the world, right? And you could predict anything for a phase transition. But the interesting problem is, what if you assume the free energy is a smooth function of the input, right? What if you assume that it's a smooth function of the order parameters? In certain circumstances, this input smooth function can give you a not smooth output, okay? And that is making a specific prediction for properties of what the phase transition can do, okay? And that works out to be a prediction that works pretty well in many experimental scenarios, okay? So, to do that here in the context of liquid crystals, okay, we're going to say, let's assume the free energy density is a smooth function of this tensor order parameter. What we mean by a smooth function is that it can be expanded as a power series about the isotropic state. Okay? So there could be a constant term, a linear term, a quadratic term, third order, fourth order, etc. Okay. So what could we make for a constant term? I don't know, it's a constant, okay, F0. What about a linear term, right? What can we do in the free energy that's linear in this Q alpha beta tensor, okay? Well, I could contract it with itself, okay? So if I want to make a scalar which is linearly proportional to this tensor, I could take the trace. That is Q alpha alpha, for those of you who know this tensor notation, okay? That means QXX plus QYY plus QZZ. Right? The good news is this thing is invariant under rotations, right? So you know as a general rule, right, the trace of any tensor is invariant under rotations, right, if you make a rotation of coordinates, okay? The bad news is this is 0, right, because that's what we were talking about before, right, that the Q by construction is designed to be a tensor with trace equal to 0, okay? What else could you do, right? Well, if you had some other vector in your problem, like a magnetic field, okay, then you could make a tensor which is, you can make a scalar which is H alpha, Q alpha beta, H beta, right? Or you could write that as H dot Q dot H, right? You could totally do that if you have a magnetic field, right? Or likewise with an electric field, okay? But suppose there isn't a magnetic field or an electric field or anything else that has a preferred orientation, okay? In that situation, this is just not available. Okay. So there's no linear term that you can make. Okay, so, okay, we'll leave the linear stuff blank. Okay, what can you do as a quadratic term? Okay, well, you could make this combination of tensor indices, right? And so this is like taking the Q matrix times the Q matrix, matrix multiplication, and then the trace of that matrix product, so the trace of Q squared. Okay, that's fine. We can put that in the list of possible terms. Okay, we could make a cubic combination like this. We could make a fourth order combination. Actually, we can make a couple different fourth order combinations like that. Okay. Now, let's put in how this Q tensor is related to the scalar order parameter and the director. Okay, so if I put that in, then I get a free energy expansion like this, right, in terms of the scalar order parameter. Okay, so it has this constant term, has no linear term. It has something that's quadratic, something that's cubic, something that's fourth order. Okay, this is the kind of expansion that you might recognize if you've seen this style of theory applied to magnetism or superconductivity. Okay, but there's a cubic term, right? Unlike in the case of magnetism or superconductivity, where you only have even terms. Okay, why a cubic term? Well, because you can construct this cubic combination of tensors, right? This goes along with having a tensor order parameter rather than a vector order parameter. Okay. The free energy, how does the free energy depend on the director? Well, it doesn't, right? I mean, there's no director here, right? The free energy is the same if you have a certain quality order in this direction or a certain quality order in this direction or whatever direction, right? So it only depends on the magnitude of the order and not the direction of the order. Okay, that's the idea of spontaneous symmetry breaking, right? That there's nothing in advance to break the symmetry. There's going to be a random selection by the system of which direction to line up the molecules. Okay. What are these coefficients, right? Well, we don't know, right? The coefficients are phenomenological, meaning we don't know them in advance, but what can we assume about them, right? Well, once again, we want to assume smoothness, right? We only want smooth things to go into the input of the theory, so that it will limit what not smooth things we can get from the output. Okay. So these things must be smooth functions of the temperature. Normally, in the study of phase transitions, the quadratic coefficient turns out to pass through zero, right? That it is positive at high temperature and becomes negative at low temperature. The others tend to be constant, right? And so in this case, I'll tell you B is a negative constant, C is a positive constant, okay? So this is, again, very much like what you might have seen in Landau theory for magnetism or superconductivity, except without the cubic term. Okay. So now let's make some sample plots of this function. Okay. So when you're at high temperature, so that A is the quadratic coefficient is a big positive number, you get a plot that looks like this, okay? It has a minimum at s equals 0, and then when s goes up, well, the quadratic piece makes the function go up, the cubic piece tends to push it down, the quartic piece tends to push it up. Okay, so there's just a single minimum at s equals 0. Okay, this is the free energy corresponding to an isotropic phase, right? If you minimize the free energy, you see a minimum at s equals 0 right there. Okay, now suppose we reduce the temperature so that the quadratic coefficient is still positive, but not so positive, not so big. Okay? In that case, the function has a minimum at 0, then the quadratic piece makes it go up, the cubic piece makes it go down, the quartic piece makes it go up again. Okay? Now, you can see that the function has another local minimum at some non-zero value of the pneumatic order. So, this is a situation where the isotropic phase is stable and the pneumatic state is metastable. Okay? This local minimum is a metastable state. Now, suppose we continue to reduce the temperature, then we reduce the quadratic coefficient. In this situation, the pneumatic minimum comes down. At a certain temperature, they have equal free energies. Okay? So, this is right at the balance point between isotropic and pneumatic. Okay? As we continue to reduce the temperature, the pneumatic state now gets lower in free energy than the isotropic state. Okay? And so here we have a phase transition from isotropic to pneumatic. Okay? And you can see that it is a first order phase transition, right? Meaning that the order parameter jumps discontinuously from 0 over here to this significantly not 0 value over here. Okay? So if we were to make a plot of that for the nematic order parameter on the vertical axis as a function of temperature on the horizontal axis, then you can see that the minimum is 0, 0, 0, 0, 0, and then it jumps discontinuously to a non-zero value, and then continues to increase as you go lower in temperature. All right, so this then is making a prediction for the isotropic nematic transition, right? It's a prediction that comes out different from the prediction that you might have seen for a magnetic order parameter or a superconducting order parameter, right? In those situations, you know, what you might have seen in the theory of magnetism is a plot that looks like this, okay? For a magnetic order parameter as a function of temperature, right? That it's 0, 0, 0, 0, 0 down to a critical temperature Tc, and then it can be either positive or negative, like that. Have some of you seen plots like this, maybe in solid-state physics classes, right? And so here, the plot shows the magnitude of the order, which is the absolute value of m, which is increasing like this, approximately as a square root law. And then the direction can be positive or negative, okay? What I have up there is the analogous plot for a nematic liquid crystal, okay? And it's different. This one is second order, meaning that the order parameter is continuous, but the derivative of the order parameter is discontinuous, okay? Whereas the one up there is first order, meaning that the order parameter itself is discontinuous. And so, you know, that is a prediction which comes just from thinking about the symmetry of the transition without needing further input about molecular aspects of the transition. Question?
Yeah, so it's about like that plot right there. I'm assuming there's something in the Landau functional for the ferromagnet that does not allow the cubic term, right? So that the transition can be. What is it in the for the ferromagnet that bans the cubic term, and why is it allowed in the for the nematic?
Well, just a symmetry between m and negative m. Right? So if you have a vector order, right, then you have to have a symmetry from n to negative n, right? And so, you know, if you are dealing with an Ising type order, right, then, you know, positive and negative are your only possibilities. If you're dealing with a magnet that can order in any direction in three-dimensional space, then you want a vector for the magnetization, and you can say, well, how do you make vector terms? How do you make a free energy scalar out of a vector, right? Well, you could have the vector squared, or you could have the vector to the fourth power, but there's no analytic way to put a third order term in there, right? Whereas there is an analytic way to get a third order term when you're dealing with a tensor of rank 2 like this, right? And so, you know, that's a payoff of thinking about the symmetry, is getting this aspect.